In the world of Dota 2, there are two factions, the Radiant and the Dire. These factions are represented by senators in the Dota 2 Senate, where they must decide on important changes to the game. The decision-making process is round-based, and in each round, a senator has the power to either ban another senator's rights or announce the victory for their party if all remaining senators with voting rights are from their party. The problem is to predict which party, Radiant or Dire, will ultimately announce victory given the initial configuration of senators. This configuration is provided as a string where each character represents a senator's party. R for Radiant and D for Dire. The size of the string corresponds to the number of senators. To solve this problem, the algorithm uses two queues to simulate a round-based voting procedure. One queue is used for Radiant senators and the other for Dire senators. Each queue stores the indices of the senators in the initial string, representing their positions in the round order. This setup ensures that the senators are processed in the correct sequence as per the rules. The first step is to populate these queues. As I iterate through the string, if a senator belongs to the Radiant party, I push their index into the Radiant queue. Similarly, if a senator belongs to the Dire party, their index is pushed into the Dire queue. This sets up the initial state for the round-based voting process. The voting procedure is simulated in a loop that continues until one of the queues is empty. In each iteration of the loop, I compare the front elements of both queues, which represent the current senators from each party who are ready to act. The senator with the smaller index, meaning who comes earlier in the round, gets to exercise their power first. If a Radiant senator's index is smaller than the Dire senator's index, the Radiant senator bans the Dire senator's rights. Consequently, the Radiant senator having exercised their power will get another turn in the next round. To simulate this, I add the Radiant senator's index plus the size of the Senate to the Radiant queue, representing their position in the next round. The Dire senator is removed from the Dire queue and loses all future rights. Conversely, if the Dire senator's index is smaller, the Dire senator bans the Radiant senator's rights. The Dire senator is then pushed back into the Dire queue with their index plus the size of the Senate representing their position in the next round, while the Radiant senator is removed from the Radiant queue. This process continues, with senators being removed or re-added to their respective queues based on their actions until one of the queues is empty. If the Radiant queue is empty, it means all Radiant senators have been banned and the Dire party announces victory. Conversely, if the Dire queue is empty, the Radiant party announces victory. The algorithm ensures that each senator plays optimally for their party by always acting as soon as they are able and banning an opposing senator whenever possible. This greedy approach ensures that the game state evolves correctly according to the rules described. Each senator's decision to ban the most immediate threat, the next senator from the opposite party, maximizes their party's chance of winning. By using queues to manage the round-based voting process, the algorithm efficiently simulates the decision-making procedure of the Dota 2 Senate. It predicts which party will ultimately prevail based on the initial configuration of senators. The solution is both elegant and efficient, leveraging the properties of queues to handle the dynamic nature of the problem. By continuously comparing and updating the positions of senators, the algorithm accurately determines whether the Radiant or Dire party will be able to announce victory and implement their desired changes in the game. In conclusion, the problem of predicting the winning party in the Dota 2 Senate voting process is effectively solved using a queue-based approach. This method allows for efficient handling of the senators' actions and the dynamic changes in their rights throughout the voting rounds. The solution ensures that each party's strategy is optimized, leading to a clear prediction of the winning party. Now, let's test this code to ensure it works as expected before submitting it. Remember to explore different algorithms and implementations to potentially find a more efficient solution.